Welcome to Chattanooga, everybody. Yeah, come on. Why not? Why not? It's Thursday. Yeah, so gonna just power through this. Next week, come out. We've got a bit of a treat for you. Aaron Gustafson is gonna be hot mic. Aaron Gustafson is gonna be coming to talk to us about headless user interfaces and designing conversations using voice. And how that all figures into building on the modern web. So that'll be a fun talk. Won't piddle around here. Why don't you guys just go ahead and give it up for Derik. Round of applause. There we go.
All right, can you guys hear me? Yeah, there it is. All right, awesome. So I am Derik Pell. I have just lost video. There we go. All right. I'm Derik Pell. I'm an engineer at Emma Email Marketing. I'm working remotely here in Chattanooga. We're actually based out of Nashville. So that's me. The talk is bringing functional programming to an imperative world. Maybe. You can't see the maybe down there. It got cut off. I wrote these slides on my personal laptop. I swear it worked on my machine, right? How many times do we hear that? So this was actually written specifically for PyTennessee conference, so it's very Python heavy. Do we have any other Python developers? Yeah, a couple of you guys? Awesome. Yeah, Justin, I know. So it is written, the presentation's written for Python, but most of what I'll be going over is available in most modern programming languages. So if you do JavaScript or Ruby, I checked those out. There are, analogs to most of what I'm going over in those languages. The purpose of this talk was really to sort of introduce people who work in a more imperative environment that don't get to play around with functional programming, introduce functional concepts so that, at its core, functional programming is really more of a way of thinking about how to do your code. There are languages that help you do that a lot, and there are languages that work against you. Languages like Python sort of sit right in the middle. They have some really good built-in tools that let you do some amount of functional thinking. They have some problems when you try to get too deep into the functional weeds. So we'll try to look at that and go over some of those details. Why functional programming? Well, if you actually get to work in a more functional language, functional programming is very expressive. You can do a lot with a very little amount of code. Typically, it's very efficient. You can do things very quickly because of the way functional programming thinks. It's a lot safer. It's not completely safe, it's not bug-free, but you can help eliminate certain classes of bugs when you are able to fully embrace functional programming. And it's a lot easier to work with concurrent programming, which is becoming more and more of a necessity as we build out multiple cores in our machines and we try to work across machines and things like that. So there really are a lot of benefits to functional programming. It is not just a buzzword, and it's not just like, oh, let's try something new. Like there are some valid reasons for using functional programming. So let's start talking about some of the pillars of functional programming. One of the core pillars, one of the things you almost absolutely need to do any type of functional programming are higher order functions, right? So higher order functions just means that you can pass a function around just like you would any other type of variable, right? You can pass it into you can pass a function into a function, you can return a function from a function. They're pretty much just first-class citizens. And that's something, as we start looking at some code samples, that's really very necessary to get any type of real benefit out of functional programming. Another pillar is, are immutable data structures. So most of us work with mutable data on a day-to-day basis. That's, the bread and butter of object-oriented programming is working with mutable data, things that you can easily change in line. But that's where a lot of bugs sneak in, right? Like you pass a data structure along and someone changes it somewhere and you're not expecting it to change and it changes out from under you, and what you have is not what you started with. With immutable data structures, if you're not used to working with those, the structure itself never gets changed. You create a list, you pass that list along, that list never gets changed. That you can be assured that whatever you pass to someone else, whatever they do to it, it's not going to change your list because your list is immutable. Because data structures are immutable in this way, you have to think about updating them in a different way. You have to really sort of shift your mindset, and we'll talk a little bit about recursion, and that's one of the key elements to updating and playing with immutable data structures. The reason is every time you update an immutable data structure, what you actually get back is a brand new data structure. You aren't taking the original list and adding to it or deleting from it. You're taking the original list, adding some element, and bringing an entire new list back that's just the original with the new element added or deleted. That gives you a lot of safety. Like I said, you can make sure that your data structure does not change out from under you. Historically, immutable data structures have been very inefficient because what you need to do to get that immutability is make a complete deep copy of your data structure. And if you have a very large data structure with a lot of elements, or it's very nested, then that is a really expensive undertaking. More modern immutable data structures use something called a persistent data structure. Is anyone familiar with persistent? A little bit? All right. So persistent data structures are basically, it's a new way of organizing data structures. And I know for instance, in Clojure, what they do is they model the data structure as a tree with a branching factor of like 32, I think. So it's like a very wide, very shallow tree. And they make pointers. So you create your initial list, you have your initial tree, and then when you need to update that list, instead of creating a whole new list, it creates pointers to parts of that list very efficiently. So you actually keep the bulk of your original data structure in place, even though what you're getting back is a new data structure that has, your initial 10 elements plus a pointer to this new element type thing. And so behind the scenes, it's very, very efficient. I know in Python, someone has been writing a library for this. I believe in JavaScript they're doing that. I'm not so sure about Ruby. But in any case, that's sort of the new way of doing immutable data structures. And so in your language, if you want to check out immutable data structures, you should look into that because you really don't want to try and do this, make something immutable in your language if it doesn't support an efficient, persistent data structure. Otherwise, you will waste a lot of cycles trying to make copies of stuff. If you need the safety, then that's a trade-off you have to decide to make. One of the other pillars, of course, is recursion. Recursion is one of those things where, more than likely you ran across it in a programming class and maybe never went back to it again because it is incredibly inefficient in almost all languages that don't think functionally, because you don't really have to use recursion. You have to get recursion to work efficiently. Well, let's just go down. So recursion is a function which calls itself from within the function, right? So if you've ever done something like the Fibonacci sequence inside, if you ever wrote like a little program to do that, somewhere along the line you create a function called Fibonacci, and then within that function you call back into Fibonacci, passing it some various variables and some changes and things like that. So basically recursion is just calling the same function from within itself. It takes the place of loops in most functional languages. So a lot of functional languages either don't have loops or you don't really use loops all that often. What you do is you recursively call back into itself, making a change to your initial state, calling back in to your recursive function with its state changes and whatnot. The problem is that every time you make that recursive call, it typically adds to your call stack. at least in languages that aren't optimized. So every time you call back into your call stack, you add to that stack, you add back into your call stack, and you run the risk of blowing through your stack, right, and running out of memory. Some languages have a hard limit or a predetermined limit on how big your stack can get. Python, you can only add 1,000 frames to your stack. You can override that, but by default, it's 1,000 frames. So it's really easy if you were to try to recursively go through a moderately sized list, then you could go through your frame stack really quickly in a language like Python. And going through a list recursively is the way you typically update a list in more functional languages. So you will take your list, you will want to add something to it. What you'll do is you'll throw your initial list and whatever you want to add back into the recursive function, and then it will continuously add to that list. And when the list unwinds, when the recursive function unwinds, what you get is your new list, in whatever format, with whatever you've added to it. And we'll sort of look at an example of that once we get to the code part. So hopefully it'll make a little more sense. But some languages have tail call optimizations, which if the last thing you do in your function is the recursive call back to the function, then the language compiler can go in and do some optimizations and eliminate all those call stack, eliminate increasing your stack. It can just say, okay, well, I have this existing stack. Let's just overwrite the existing stack with these new variables because it doesn't matter, because it's been optimized because you're not holding on to any other state. If you don't write your function properly and you have some bit of state that the recursive call needs to hold on to, then the optimizations don't work and it starts adding to your stack again. So recursion's really great way to think about how to use immutable data structures, but if your language doesn't support it, and Python doesn't support it, and from what I've seen, I know that Ruby, you can get around it, I think, in Ruby, maybe in JavaScript, but it wasn't really, these languages weren't really built for that type of optimization, so it's not there by default. So you have a little more trouble trying to get recursion to work well. Another pillar are pure functions. For a function to be pure, it needs to have no side effects. It needs to be idempotent, which is just a fancy way of saying every time you give it a set of parameters, it will always give you back the exact same return value. You always give it this set of parameters, it will always give you that same return value back. So for instance, if I always give it a list of 10 numbers and ask a function to give me back all of the even numbers, if I give it the same 10 numbers every time, I'll get the same even numbers back every time. A function that is not idempotent is somewhere in there, it might have to check the date, right? So if it checks the date, or if it does something with the date, that date could be changing every time, so you could always get something different back. So that would not be a pure function. And pure functions are great because they tend to be very small. They tend to be very clean. It sort of enforces the idea that each function does one thing and only one thing, right? So it's really easy to break up your code when you start thinking about it in pure functions and try to push that we can't always work in pure functions. Sometimes we have to work with dates and things like that. If you can push that further out, and set that as its own function, your core functions can be more pure, and they're much easier to reason about. They're much smaller, and they're so much easier to test because you don't have to worry about all these weird side conditions and things like that. So if nothing else, if you can't do anything else with functional programming in your language, try to think in terms of pure functions and try to get most of your functions to have no side effects when possible, to be idempotent. They're so much easier to work with. Function composition is just combining functions the way you would in math, right? So you basically call you take a function and compose that with another function such that the return value of the first function becomes the parameter of the second function, right? So that third bullet point, f of g of x, If anyone remembers their, I guess it's algebra. I'm terrible at math. Calculus? Sure, whatever. Some form of math that I don't have to do on a daily basis, luckily. In any case, yeah, so it's basically just because if your functions are composable, you could do the f of g of x, or you could reverse it and do the g of f of x, so that your f function returns and is an input to your g function. And this is something that we probably do on a daily basis, but don't really think about it. You might, call a function and assign the return value to a variable, then send that variable into the next function, that type of thing. That's just composability. It's a pretty simple concept. And these are the holy trinity of functional programming: map, reduce, and filter. And we'll look at some examples of these a little further along. But these are the core built-in functions that you end up using quite a bit because they're very helpful. They do a lot for you. Map is where you take a function and apply that function to some sort of collection, and map will go through and apply that function to each item in the collection in order, whatever order means depending on the collection, I suppose. But yeah, so you map over a collection, you apply the same function to the collection over and over again, and what you get back then is a collection that has the original values. The return value is a collection with the function applied to the original values, right? So if you want to go through and just multiply every value in a list by 10, what you get back is a list where everything was already multiplied by 10. Reduce is where you take and apply a function to a collection, but it gathers everything down into one final variable, or one final value, right? So you don't get back a list, you get back one item. And we'll see an example of this, but the kind of classic example is you take a list of numbers and you can reduce them down using like an addition function, and you can reduce them down to whatever the sum of the numbers are, right? Filter is applying a function to every item in a collection, and we're seeing a pattern here, right? Where you apply the function to the collection, you get a new list back that has filtered the collection down for you. So the filtering function actually needs to be return a true false value, right? So anything in that function that returns true, that item gets put into the new list. If it returns false, that item gets eliminated from the new list. So list of 10 numbers, you want to get all the even numbers, you can filter them down using a quick little function that will check for whether or not they're even and give you back a list of nothing but the even numbers. A helpful little tool in doing map, filter, and reduce are lambdas, or anonymous functions, or unnamed functions. They're just little typically one-liners, something that's very quick that you don't have to like write out a whole definition for and whatnot. You can just sort of throw it in line most times and kind of quickly have your whole map, filter, or reduce right there in one line. So before we start getting into the actual details of Python, in this case, Python is not a functional language. And a lot of the languages that you work with are probably not functional languages. They may have a lot of tools that let you do functional stuff. I know JavaScript has like underscore or Lodash that have a lot of functional type functions, methods inside them. And those are really great because what they've done is abstracted away all the ugly details for you so that you don't have to worry about how to implement this in a very functional way. It's just implemented for you, right? So, but you need to remember that you're probably not working in a functional language, or if you are, you absolutely know you're working in a functional language. Python is not. So why would we do functional programming in Python? Python has most of what we need for functional programming, so we get a lot of the benefits already built in. Functions are first-class citizens. There are ways of working with immutable data or ways of making it look like you're working with immutable data. Map, filter, and reduce are built in. We have lambdas, so we have a lot of the pillars that we already need. And again, probably your language has some, if not all of these in some format or another. So, you know, if you need to do a little research, it might be worth your time to figure this out. Which, again, this is all Python specific, so, you know, not relevant to the entire crowd. We have immutable data structures, which in Python, tuples, strings, numeric types, frozen sets, and bytes. Tuples in Python are immutable. They're a list of mixed type. You can put any types in there that you like, but if you want, you can't change them in place. You have to create a brand new tuple to make an addition or a subtraction from it. It's unlike a list. The list in Python is mutable. To work with immutable data, you have to make this deep copy. Like I said, it can be very expensive. But we also have comprehensions, and I know a lot of other languages have comprehensions. Comprehensions are a really good way to mimic working within a mutable data structure, because as we'll see, when you do a comprehension, you actually get a brand new list back. You are not working on the list that you started with. But comprehensions are actually very fast and efficient in Python. When Guido, we all call him Guido, right? The guy who invented Python, when he made very specific choices to give people things like comprehensions so that they didn't have to ask for map, filter, and reduce, because you can do a lot of that kind of stuff with a comprehension. They've made a compromise. We have comprehensions, but we also have map, filter, and reduce in there. Recursion in Python, and I imagine this is similar in whatever language you're in. Every time you call it, you add to the stack. There is no tail call optimization in Python. There are ways to write your functions that are recursive, that kind of get around that, but they're not very elegant, and so they're probably not worth pursuing. So recursion in Python is probably not something you want to explore. Again, that was a very specific decision made by Guido. If you do tail call optimizations, you lose that history of your stack, right? Like, you don't know if you have a problem somewhere deep in your stack, in what would be your stack, then you've lost all that information, because all you get is that one stack frame, as the optimization reduces everything down to that one frame. So Guido decided it's better to have the entire stack frame available rather than do tail call optimization. We do have map, filter, reduce, lambdas, all that type of stuff. You know, actually though, instead of doing that, let's just go here and start looking at some code. Can everyone read this? Do I need to bump it up? Bump it up a bit. Maybe I can. There we go. Better? A little bit? We're all right? One more? We're good? All right. This is, if you've never worked in IPython Notebook, this is actually called Jupyter Notebook now. Jupyter Notebooks are amazing, and they're almost certainly one for whatever language you work in. I would check them out. If you have any questions about this, ask me afterwards. This is all stored in a JSON file behind the scenes. You tie it into some type of compiler or interpreter, and then you can put code in here and run it and save it and hand it off to people. I always try to pitch Jupyter Notebooks. So here we have an example of higher order functions, right? We've created a function called adder and a function called add2, because naming things is hard. And essentially what we're doing is we're taking adder, passing it a variable, and then passing the return value of that back into add. Sorry, I got myself confused. And this is, it can be a little confusing sometimes. If you don't work with this kind of stuff on a daily basis, and I don't, then it can get a little mind-bendy. We're taking adder with a value of 3 as its initial value, and passing that whole thing into add2 as its function there, right? So add2 takes a function and a number, and it basically takes that, in this case, what we're doing is we're adding 2 to every number that we pass into adder, right? So what we get back is 5. So we started off with 3, and adder takes 2 numbers and adds them together, but we don't give it both numbers. We're only giving it the first number. Add 2 then takes that function and actually applies the second number to it. In this case, it's 2, so that any number we then put here will get 2 added to it, right? And so this is higher order functions because we're passing the function adder into the function add2, right? And down here, same type of thing, but in this case, we have another function called add2 that has an inner function called inner, and that's, when we call add2, we're actually returning the inner function. So in this case, instead of passing a function in, we're returning a function as the return value. And so, if you're not, I forgot to mention, this is the return value right here, right? This is the result of running this code. So we are taking the value, so we've created, we've assigned x, or adder 2, to the variable x, which turns x into a function. We're passing it these 2 variables, 3 and 4. Adder 2 then returns this inner function, which we end up calling here just like any other function. So we've basically given back a function that we can then call and pass around as needed. If you have any questions, by the way, along the way, just raise your hand and ask, and I will do my best to answer them. So that's, those are higher order functions. The next pillar would be immutable data structures. So there are, of course, some problems with immutable data structures. One of which is right here. We create a list of 4 values. We assign list 2 to list 1. Then we change list 1, and it has changed list 2 along the way, right? Because we created a list, and we created 2 pointers to the same list. So we've created them. The last print statement there, list 1 is list 2. That's Python's comparison, and it's true that list 1 is list 2. So here we see, we have this one object that you may pass it in. I may reassign it to a new variable, but because it's the same list, if I make any changes, whatever you have, my changes percolate up to your list. So that's one of the problems that we have with immutable data structures. With mutable data structures. Working with immutable data structures kind of helps alleviate that problem somewhat. You can see in the top part, we take a list. We're pretty much doing the same thing we did above. We validate that both lists are pointing to the same thing. In the second part, though, we take a list, and that's a comprehension. We'll look a little more at a comprehension later on, but essentially what that's doing is that's creating a brand new list, right? We're assigning it back to list 1, but instead of changing what the original list 1 in place, this is actually creating a brand new list, bringing it back, and you can see down here at the very bottom what we've done. Even though we made changes to list 1, because we created a brand new list, list 1 and list 2 are no longer the same list, right? We get a false here when we try to compare them. So this is a much safer way of working with lists. It's technically not an immutable data structure. It's creating a brand new structure on the back end. But because the comprehensions are very efficient, this is actually a really good way to do this type of thing in Python. So you give me a list, and instead of manipulating that list in place, I manipulate that list with a comprehension. And then that lets me bring back a brand new list, and everybody's safe. Your list doesn't change. I get what I need out of my list. Make sense? Tuples, again, are another way of dealing with immutable data in Python. But as you can see, we actually, this plus sign right there is adding 4 to the tuple x. Up here is the tuple x, right? And Python has some very odd syntax for working with tuples. Like, I can create a tuple this way with nothing around it, but then if I want to create a one-item tuple, then I have to put it in parentheses with just a comma. It's a little weird. But in any case, what Y is doing is taking the original tuple, adding 4 to it. Behind the scenes, it's actually making a deep copy. So this is not very efficient, and this is not the kind of thing that you would want to do, because it is making this sort of deep copy of your entire tuple. But it's a safe way of working with data so that you don't mutate it along the way. So again, it's one of those trade-offs. If you need to do it, that's the way you need to do it. So this is, let's talk about recursion. Everybody good with mutable, immutable data? All right, awesome. So recursion. As you can see here, the method is called factorial. This is sort of a standard way of doing it, where you call factorial on itself with, you start off with n, then you call it back with n minus 1. You multiply n times the new factorial of n minus 1. You print it all out. You start off with factorial 5. You run it, and this is what prints out. All right, this is it. That was what you got. There we go. Okay. So yeah, that's sort of what you get. You know, it's a really easy way. It makes really straightforward sense as far as making the algorithm goes. This is a great way to do it. This is sort of how you would do it in your head. But the problem is, you add all of this to the call stack. Each one of these is its own stack. And so by the time you actually get down here to the base case, or the base case where you are sort of completing your factorial call, you have 5 frames on your stack already. And this can actually get even worse if you do Fibonacci. It adds multiple frames and you're doing the same calculations over and over again. So you have a lot of frames that are doing the exact same thing. I swear I'm not doing that. So in any case, it's really inefficient if you don't have tail call optimization, right? So this is the problem that can happen if you try to do recursion in a language that is not built for it. This is actually not the best way, even if it were tail call optimized. This is not the way you would write this, but it's not worth writing it properly because we don't have optimization in Python. You would want to write it so that it doesn't hold on to state right here. You would actually do that calculation inside the call back to factorial. But irrelevant in this case. Any questions about that? We're good? Awesome. So that's actually really something that you have to watch out for if you start trying to do any type of functional hoodoo in your language. Check whether or not it's tail call optimized before you get yourself into a lot of trouble. All right, and so we'll look into the Holy Trinity here. So first off, let's start with lambdas. Lambdas, like I said, are anonymous, unnamed functions, right? So we're taking the variable sum and we're assigning a lambda to it. And a lambda is, in this particular case, the syntax is lambda, and then the parameters, x and y, and then colon, and then the actual function calculation that you want to do. And typically, they're one-liners. They're going to be very short like this. It doesn't make any sense to try and do a more complicated function inside a lambda. They're built for these short things. So there we go. We assign sum, then we can call sum just like any other function, right? We pass it its variables. You end up using lambdas a lot when you do things inside map, filter, and reduce. In Python, map and filter both return an iterable, so it doesn't return an actual list. So you can see here, I am actually forcing it to be a list. But you may or may, that's in Python 3. In Python 2, I don't have that problem. So your mileage may vary also. But essentially what we're doing is we're taking the built-in function map, passing it whatever function we want to map over this list, right? So it's going to take that, what it'll do is take the first item in the list, which is number 1, and it will read it as its X variable and then do whatever calculation we ask it to do in there. So what we will get back eventually is a list that has multiplied 2 by every item in it, right? So that's how map works. And it doesn't have to be a lambda. You could have a much more complex function, but you would probably want to break that out into its own function. And as the first parameter to map, you would just call the function instead of calling it a lambda. Filter works along the same lines. Like I said, what filter has to do is it has to return a true or false, right? To decide whether or not the item that is currently on deck gets put into the new list or not. So in this case, we are just looking to determine whether or not that item is an even number, right? So it'll go through every item in our list and give us back the ones that are true for this situation. For this when this condition is true, that item gets put into the new list. So it'll start with 1. The condition is false, so it doesn't get put into the list. 2 is true, 3 is false, 4 is true. Those two make sense? All right. Reduce is not a built into the core language of Python 3. You have to actually import it. Python 3 has a whole library of functional tools, which are really great if you want to try to explore functional programming in Python. So like we talked about earlier, reduce will take a list, takes a function and a list, and does whatever calculation you need to do to reduce that list down to 1 value. So what it will actually do, previously, the other 2 lambdas in map and filter took one, it took 1 value, right, and did something with that 1 value. In this case, the function needs to take 2 values, or at least needs to have, well, it needs to take 2 values because what reduce will do is take the first 2 items of your list, right? It'll start with number 1 and number 2. It'll bring those in as x and y, do its reducing function, its reducing calculation. Then it'll take that value, and that value becomes the x, and the next value in your list becomes the y, right? So it'll start off with 1 and 2, add those, multiply those together, take that product and bring in 3, multiply that in, bring in 4, multiply that in. So you get 24. You can actually even start with, there's another version of reduce that lets you start with an initial value. So instead of taking the first item in the list as the initial value, it is now going to take 100 as the initial value. And when we run that, we get 2400 because it starts off multiplying 1 times 100 and then starts to multiply it as we go along that way. And of course, you don't, like I said, you don't have to use lambdas. You can actually use functions, right? So in this case, we want to look for whether or not a number is a prime number. We give it a list of 10 numbers. And instead of calling into a lambda here in the filter, we just call is prime. We call it by name. We don't actually call it itself, so we don't have to add the parentheses around it. But then it filters out every number that is not a prime number, right? So that way we can have a much more complex function to do our filtering or our mapping or reducing if we need to. Probably should have moved that up. But one of the things that I always have a problem with reduce is like finding really good examples. Like figuring out how to do math problems, that's pretty straightforward, and that's something you see a lot of. I came across this one, I thought it was really great. So what this does is the first line is taking a list of DNA sequences, I guess. And it's got 3 items in the list, right? So we want to go through and count how many A's there are in this list. So this is a lambda that simply takes A as the first value, X as the second value, and then it will add those two together. So since we're starting with an initial value of 0, right, and we're passing it the list DNA, the first A is 0, the first X is just a count of A's. So it goes through, counts all the A's in this first list, in this first string. Then it'll take the second string, it'll take whatever that number is, move it back up to its new A value, and then count the capital A's in the next list and the capital A's in the last list. And so this is a really quick, efficient way to get a count of, a particular letter in a string or a particular string in a list of strings, things like that. So there are some really good uses for reduce, but they're a little hard to find. I think if you do this more often, like you probably see them every day, like, oh yeah, I could totally use a reducer there, but I don't get to do that, so I have to kind of look around for good examples. But does that make sense, what we're doing there? Okay. Quickly, just to kind of finish up here, like I said, we have these built-ins, but you can do a lot of the same kind of stuff with comprehensions. My guess is you can do the same thing with comprehensions in your languages if they have comprehensions. So just to let you know, this is a list comprehension. Lists in Python are in square brackets. And all this does is say, okay, for every X in list 1, I want you to run this lambda on every item in that list. So what a comprehension does is it takes a loop, basically, and kind of moves every bit of the loop into the comprehension. And when I first figured out how to do this in Python, that blew my world apart. It was great because I took like an 8-line loop that I was doing and was like, wait, 1 line, I got it all into 1 line. Comprehensions are awesome, and if you have them in your language, I would definitely look into them. But also if the lambda is too ugly, you don't have to use a lambda. You can do the same thing we did before, just call a function on it. Same type of thing in filter. We actually use comprehensions a lot in Python. So this is a way that you can, like down here, this last item isn't using a map, or it isn't using a lambda. It's filtering just complete. All the logic is completely contained within the comprehension itself, right? So it's all self-contained. So the maybe part of this is, is it a good idea to do this? And I'm not always sure that it is. Even if you put efficiencies aside, if you aren't used to scrolling down and seeing something like this in your code, if your coworkers aren't using filter, if they're not using map, if they're not doing these types of things, it's incredibly jarring. When I first started running into this in our code base, because we have someone who likes to do this kind of thing in our code base, it takes a while. Like I can look at a comprehension and immediately scan it and figure out what it's supposed to do, but if I started looking at some lambda function where he was doing a reduce, I'm like, wait, I got to take some time to parse this. So it can be very jarring for your coworkers. If you're working in your, if you're the only person in your code base, go for it. But if you have other people, then you probably need to work it out with your team. Is this a good idea? Do we want to start thinking along these lines? Because you do have to think in completely different ways to get real benefit out of trying to move to a more functional mindset in an imperative language. So yeah, that's what I've got. Any questions? Thanks.
Isn't idempotent a little bit more than just the function returns the same thing, for the same parameter? Because, square root always returns the square root of whatever number. Mm-hmm. But, it's tied into sort of transactions. because, I mean, when I think of idempotent, it's like when I pay with my credit card. The store that took my credit card, no matter how many times it submits that charge, I'm only going to get charged one.
Right, yes, thank you, yes. So that's definitely a fuller definition. An idempotent means exactly that type of thing. You're only going to run, like, if that function runs, you're not going to rerun the same transaction multiple times and kind of screw up your database or that type of thing.
Okay.
Yes, thank you.
So I've recently gotten into Node.js, and I've been learning how to write some personal applications for that. Do you see functional programming like taking a place in Node.js?
Yeah, actually, Node is, I mean, well, any JavaScript is a place where functional programming is really taking root in an imperative language. So Lodash, like I mentioned earlier, is a library that has a lot of functional methods in it, and so I would definitely look into Lodash. I don't know beyond, like that's the library that I see most often, but there are like JavaScript's really flexible, so there are really great ways to, like, once you understand the core language, to like, oh wow, instead of doing this big loop, I can do it in this other way that's more a functional mindset, right? So like I said at the beginning, thinking in functional programming terms is really a different way of thinking about your code. It's just whether or not your tools help you do that.
Right. I'm not sure about the immutability of the functions, but I know callbacks there and
Yeah,
there's Immutable.js is an immutable library I have not worked with, but I know that it might be pretty good. So yeah.
I was going to say, follow up to that, so Node, and really, because Node is using ES6 and now some like ES7 stuff, and just in the browser, most modern green browsers are using, they have like map, reduce, all that filter built into any array. So you, so you can totally use that you don't have to use a library in Node and most browser JS.
Yeah, that's true. Yeah. We use a lot of underscore at work, but yeah, there's a lot of that is sort of built into your data structures.
I just want to comment that ES6, part of the standard, does include tail call recursion, but right now I think Safari is the only browser that actually implements it.
Okay.
In Chrome, it's behind a flag, and Edge they're still considering it. So.
All right, and they will be forever. So, any other questions? Awesome. Well, thanks for coming out, y'all.